next in our series of live lessons as part of CambriLearn's student support program for F1 Science. Today, we're going to be looking at the next topic, which is metals and non-metals. Just for the sake of being humorous, I've given you a few pictures illustrating what springs to mind for me when I think about metal. On the left, large chunks of various objects, and on the right, some scary looking guys playing clearly what must be heavy metal music. Okay, so when we look at the world around us, metals are evident everywhere. The majority of things around us, while they contain metals, are in fact non-metal. If you look around, consider the walls in the building around you, furniture in your room perhaps. I'm sitting at a wooden table on a wooden chair, for example. Your books, your papers, your clothes, a lot of the things around us are in fact non-metal. So it's surprising when you look at the periodic table that you see that so many of the elements are in fact metallic. And this is a fairly regular view of the periodic table. You see here the non-metals, hydrogen, and the right-hand side of the periodic table are all non-metals. In blue are all the metals. There's a huge majority there. And then of interest are the metalloids. That is this narrow strip of elements which correspond to metallic and non-metallic properties. So, we ask ourselves, what is metal? We know that metals can be hard if you consider metals like iron, molybdenum, tungsten. They are very tough metals. Metals can also be very soft. I don't expect that you guys would have had personal experience with metals like sodium, potassium, lithium, very highly reactive. You can cut them with a butter knife, and their texture, incidentally, I haven't had experience with lithium, but I have had experience with potassium and sodium. The texture is not very much different to cutting through halloumi cheese. I don't know if you guys are fond of halloumi cheese. It's got a firm but soft texture. You can cut through it quite easily. So these metals are like that. You might have come across lead, also a soft metal, and gold. Pure gold, 24 karat gold, is quite soft. So metal can be hard, soft. Metal can also be very loud and scary, especially if you're looking at characters like this. My heavens, he looks very loud and scary to me. Okay, of the 103 elements on the periodic table, only 18 are non-metal. So if we exclude the semi-metals, or as we refer to them there, the metalloids, and metalloids, if you ask me, this character looks like he might be a metalloid. He's both metal and non-metal. Okay, the elements we find that are non-metallic, it's actually only around 17% of the elements are non-metallic. So 83% are metallic. So if we consider the importance of metals in terms of their use and application, we find that it's important to make a study of these elements. Here's a stock photo I found just of a huge bunch of nails, but you get the picture. Metals. Let's move on to some key definitions. The term metal comes from the Greek word metallon. Metallon. I'm not sure if any of you guys know how to read Greek. Unfortunately, I cannot. But that's how we would say metal in Greek. And it comes from the word to mine, to quarry. Metal. So historically, that is how we got metals. We have to dig up the rock that contains a high percentage of the metal ore in question. We would then crush it and depending on the metal, use different ways to extract it from the ore. That's a topic that we'll be covering at a later stage. So, when we speak about a metal, typically we're discussing a material that, when freshly prepared, polished, or fractured, shows a lustrous appearance. In other words, metals are shiny. If you take a metal and you leave it out in the air for a long time, it will start to oxidize. It would rust on the surface. It would no longer be shiny. Also, if you take a metal and you grind it up into a powder, you'll find that it's no longer shiny either. That's why they say when it's freshly prepared. So if it's cast and polished, a metal will be shiny. Further, we speak about how metals conduct electricity and they conduct heat relatively well. This is a typical properties of a metal. They conduct heat, they conduct electricity. Interesting to point out that if you grind your metal into a powder, it will still conduct electricity and heat, but it won't conduct it as well. And that's because when you grind up the metal and it's in powder form, there is minute space between individual metal particles, and that gap interferes with conductivity. But we'll be speaking about conductivity in more detail later on in the course as well. Properties of metals. Typically we describe how they are malleable, meaning they can be hammered into thin sheets. Malleable suggests that they are moldable, or ductile, meaning that wire can be made from metals. You can stretch metal into wires. So, all of that should come to mind if we're trying to define what do we mean by the term metal. If we now consider what a non-metal is, we could say that a non-metal, it's a chemical element and it lacks the characteristics of a metal. It's not a great definition, but if we define what metal is, non-metal is whatever a metal isn't. Okay, so physically, non-metals tend to have low melting points and they tend to have low density. Non-metals are typically brittle when they're solid, and they usually have poor thermal conductivity, poor electrical conductivity. So in the elemental form, non-metals are mostly gas. Think about oxygen, nitrogen, hydrogen, the noble gases, okay? They're gaseous. Solid metals tend to have low melting points, but elements like carbon in the form of diamond can have a very high melting point. So when we say a non-metal tends to have a relatively low melting point, this depends on the physical structure. Which means that there are exceptions, but in general, non-metals follow that trend. So, moving on to the properties of metals. As we read above in the definition, the properties of metals distinguish them from other types of elements. And in general, if we consider the common properties of metals, these are the points that you need to remember, and they're the kind of thing that will crop up in exam questions. So pay attention to these, and once you've memorized them, the good news is that you can be earning marks from this information for the next couple of years to come, because they still ask this at the IG level. So learn it now, and it's going to work for you for quite a while. So the first one is that metals are malleable, can be hammered into sheets. Metals can be molded or shaped. And incidentally, that comes from the word malleus, which is Latin, and it has its root in the English word mallet. A mallet is a kind of hammer. So malleable means you can hammer it. Malleable. Okay, ductile. Ductile, well, that's the funny thing about English. Malleable relates to the word mallet, to hammer. When you're thinking ductile, what you should not be thinking is that metals are like a duck. Okay, that's not helpful at all. Ductile means that metals can be drawn onto wires. They can be stretched. Okay. Number 3 on the list of properties is that metals are good conductors of heat and electricity. We're later going to discuss why that is, but it comes down to the metallic bonding that takes place on the atomic level. The structure of a metal is based on the metal atoms. The way those metal atoms stick together, that's metallic bonding. And like I said, we'll go into this in more detail later. But just for now, remember that conduction of heat and electricity is due to the way that the atoms interact with each other. There are high melting points and high boiling points. Those are normally put together as one point. And once again, the fact that it takes a lot of energy to melt a metal and then a lot of energy to boil a metal, that comes down also to metallic bonding. It's the way the metal atoms stick together. They stick together very well, and that means it takes a lot of energy to break the bonds holding them together. If you need to put a lot of energy in, it means that you will have a high melting point, and similarly, a high boiling point. It's hard for us to even imagine the kind of temperature required to boil a metal. I'm going to guess that none of you at home, in your normal home environment, has ever even tried melting a metal. And if you have, maybe you do art and craft, you work with solder, you've been working with soft metals, you can get them to melt. But to boil a metal, to make a metal gas, that takes a huge amount of energy. And also, of course, it would be very dangerous because metal gas, it would be really hot. If you got that on your skin or if you breathed it in, the consequences for your health would be extremely, extremely dire. Okay, so don't boil and breathe metal gas at home, guys. It'll kill you. Okay, and then the last point, metals have a shiny appearance. Okay, that depends on the state of the metal. What do I mean by state? Take a chunk of shiny metal, throw it into the sea for 5 years, drag it out, it's going to be rusty and tarnished. It's not going to be shiny. But if you take something metal, like maybe you've got a, I don't know, silver bowl at home or something, and if you polish it, it'll be nice and shiny. As long as it's freshly prepared, it will stay shiny. But there are other properties that some metals have, and it's important for us to be familiar with these, and also to realize that these are metallic properties, but they don't apply to all metals. So these properties, depending on conditions like the state of the metal, all metals in general can be shiny. The best points here to use, I'm going to suggest, are actually these first ones. These are the ones that you should remember because they apply all around. Some of the metals do not actually have high melting and high boiling points. If you consider group 1 metals, and let's just go back to remind you what I'm talking about. Later on, when we study the periodic table in more detail, sorry, let's just change that pen. Group 1, Group 2, Group 3, group 4, group 5, group 6, the halogens, group 7, and the noble gases, group 8. Okay, the group 1 metals, that's all the metals in this group. They've got very low melting and boiling points. So in general, when we speak about high melting and boiling points, specifically, we're looking at the transition metals. But there are exceptions there as well, because lead has a low melting point. Mercury is a liquid at room temperature, so obviously it also has a low melting point. So, in general, metals have high melting and boiling points, but there are exceptions to them. But they're all malleable, they're all ductile, they're all good conductors of heat and electricity. Okay. So, other properties of metals that are not common to all metals: magnetism. The ferromagnetic metals, iron, and you guys should be getting familiar with the chemical symbols for each of the elements. Nickel and cobalt are able to exhibit magnetic attraction. So if you make something out of iron, nickel, cobalt, or if you mix those metals together and form an alloy, you will have a material that can be magnetized. It will store magnetic potential, and it can also exhibit magnetic attraction to other magnet materials. So magnetic materials can be magnetized, and they can act as magnets themselves. Not all metals do that. So that's why we have to make this distinction. Sonorous. As a musician, this is one of the properties of metals that to me is the most interesting and the most important. I should have looked for some symbol photograph to include here, but instead I've got this nice stock photograph of nuts and bolts and random bits of metal. Okay, some metals make a distinctive sound or tone when they're struck, and certain metal alloys, remember an alloy is a mixture of metal atoms. When you combine different metals together, one metal might have certain properties. Another metal might have its own properties. When you combine those together, the alloy has its own set of properties. You can design alloys with this in mind so that the alloys will do certain things for you. Some alloys are designed to be light and strong. Other alloys are designed to melt at low temperature. Alloys used in the development of musical instruments, you get special types of bronze made, and those can be hammered out to make bells, cymbals, gongs, that kind of thing, so that when you hit them, bong, they make a good sound, a better sound than other metals. So for instance, if you were to take a piece of lead and you were to shape it into the shape of a cymbal and you hit it, it would just make a dull funk sound. Bonk, bonk. It's a dull metal. But if you take bronze and you cast it and shape it into a cymbal and you hit it, you'll get a lovely ringing sound. So sonorous means that some metals can make distinctive sound. It's a very interesting property. Moving on to non-metals. Physically, as we said, non-metals tend to have relatively low melting point. And if you've got a low melting point, you will always have a low boiling point. Interestingly enough, these two are linked. You can't have a low melting point and then suddenly have a high boiling point. Vice versa applies as well. Non-metals also generally have low density. They're soft, they're light, they melt at low temperature. Think of things like cheese, a block of margarine, a tub of ice cream, that candle wax. These are materials that really represent the typical for non-metals. There are only a very few non-metals that are hard and have high melting points. They do exist. I mentioned diamond. You get special forms of silicon oxide as well. Silicon oxide, in nature, you'd call it sand. But if you melt it and if you mix other chemicals with it, you're able to make glass. And glass is brittle, but glass has a very high melting point and a high boiling point compared to other non-metals. And you can get specialized glasses that will have very high melting points. Industrial glassware, the sort of thing that you'd use in the laboratory. That is a glass that's designed to have a high melting point. Okay, moving on to discuss metals and non-metals in everyday life. As we discussed earlier, at first glance, when you look around you, and literally, I'm looking up, I see the wooden roof beams in the roof of the house here, walls made out of concrete and cement and stone, bricks, all of that's non-metal. So, non-metals in the pure form are not used very much, except for a few rare examples. So if you think of carbon, in its pure form, well, if you're having a barbecue, you might burn charcoal briquettes. That's a pure form of carbon. If you're making jewelry, diamond, that's pure carbon in the diamond stone. But otherwise, pure non-metals, we don't really use them that much. Sure, they're present all the way around us. Oxygen gas, for instance, we have to breathe it. It's a non-metal. It's there. But it's not that we actually use oxygen as a physical thing. So, if you think about the natural materials around us and what they are made of, mostly we're going to find that it's non-metals making up these materials. We discussed wood being used for furniture and paper, cotton and wool, basically just processed. Cotton is a processed plant, wool harvested from sheep, making up our fabrics. Brick, stone, concrete, these are all examples of non-metals. Plastics, glass, we touched on those as well. Also, non-metallic. Metals, on the other hand, are very useful because they can be shaped. And we've discussed how by making alloys, you can get different physical properties. And that means that you can design alloys to fit certain purposes. Useful because then you're able to make materials to serve certain ends.
So, let's start. The simplest atom that we have, here we've got a periodic table. The simplest atom that we have is that of hydrogen. So hydrogen looks like this. So we've got hydrogen over here. And hydrogen has a single positive proton in the center and a single electron floating around the proton. Let me just put that in different colors. Here we go. Orange for electrons. So a single electron floating around the proton. So this is the simplest atom we've got. Our next simplest atom we get is helium. So helium, we need to go look over here again. So helium, we've got over here, helium has 2 electrons and 2 protons. That is this number that we see in the top over there. And it's got an atomic weight of 4, which means that it's got some neutrons as well. So helium looks like this. It's got 2 positive protons in the center, and it's got 2 neutral neutrons. I'm just going to mark them an N. And then, floating around it, it's got 2 negative electrons. So this is what helium looks like. So we have, from what you can see here, 3 different subatomic particles. We've got protons, which are positively charged. We've got electrons, which are negatively charged. And then we have neutrons. They're neutral, but they do contribute to the weight of our atom. So these are our simplest kinds of atoms that we can draw. But now we get into a bit of a problem. How do we draw all of the rest of these things? How about sodium and all of these other kinds of stuff? So here is our trick. Our orbitals that we have can only support a finite amount of electrons. So for our first orbital, it only goes up to helium, so it can only support 2 electrons. So here we go. This is our first orbital. So our first orbital can have only 2 electrons in it. Then it's full, and it can't carry anymore. So now, if we want to have another electron into this, say, atom, then the electron will not be able to go and sit in this orbital. It'll have to go sit in the next orbital around. So our second orbital can hold a total of 8 electrons. So when our second orbital is full, that means we've got a grand total of 10 electrons in our atom. So if we go look at our periodic table, we can see the one just below helium is neon, and neon has 10 electrons in its atom over there. So these all down here are what we call our noble gases. So our noble gases are kind of special. Since their orbitals are full, they can't bind to anything else. They can't be divided into smaller bits, and they can't make up bigger molecules. The rest of our atoms that we have can actually bind together in certain ways in order to make different kinds of atoms. So you will only need to be able to draw atoms up to calcium over here. So it will only have 2 electrons in its 4th orbital. And we know this by looking over here at these numbers over here. So these show us pretty much the orbital that we're working with. So this is our first orbital, and in our first orbital, we only have hydrogen and helium that can sort of work there. In our second orbital, up to where it's full, we've got all of these. They still have electrons in their first orbital as well. So you will only need to be able to go up to calcium over here. So it'll have 2 electrons in its 4th orbital.